Hello. Here we are going to cover mastery topic number 3, exponential and logarithmic functions. Okay, these problems will parallel a lot of the problems on the summer math packet, but they are a little different. These are to be used as supplemental information to help you out. So, starting with the first one, simplify completely. The reason one of these looks incorrect, or you can't leave it like this, is because, well, you have multiple x's and then multiple exponents. You should have one value of x with only one exponent. So in this case, we will write something like, okay, if we took that first one, can we simplify the inside? It would be x to the 7th over x to the negative 5th. Well, one thing we can do is we can take a negative exponent and take it to the other side. Well, if we bring them together, x to the 7th times x to the 5th, that equals x to the 12th. Okay? When we are multiplying two x's, we add up the exponents. Now, when we look at this remaining term, which is the 1/3 exponent, when I take x to the 12th to the 1/3, the rule for power to a power, that's multiply. So 12 times 1/3 is x to the 4th. So our final answer here is x to the 4th. Very similarly in number 2, okay, we have a few pieces, so we're actually going to simplify each one of these pieces separately. The first piece, x to the 3rd to the 6th, again, power to a power, you can multiply, so that gives us x to the 18th. And I'm even going to do that here. I'm going to have x to the negative 15th and y to the 3rd. Now, all of these are being multiplied. There is no distribution. You only use distribution if I have addition or subtraction. Since there's no addition or subtraction, I look at this and I say, okay, how can I combine like terms in a sense? For example, how can I combine x to the 18th and x to the negative 15th? Well, again, if I'm multiplying two x's, I add up the exponents. So 18 and negative 15 gives me to the 3rd, but there's nothing to combine with the y, so then my final answer is x to the 3rd, y to the 3rd. All right, number 2. Next, rewrite each of the following expressions in radical notation. That means currently we have x to the power of a number. We want to rewrite that as the root of x to some exponent right there. So rather than having a decimal or fraction inside the exponent, we want to have it in radical notation. First thing, always a suggestion, is rewrite this as a improper fraction. Now, if I look at this, 3.25 is the same thing as 3 1/4, which is also equal to, let's see, 3 times 4 is 12, 13/4. So if I was to rewrite this as like an intermediate step, it would be x to the power of 13/4. If I'm ever converting x to the power of 13/4 into radical notation, the number on the bottom, this number, is the same as the index. So we would write the 4th root of x to the 13th, like that. Same thing on this one. If I have x to the negative 0.6, so we'll deal with the negative in a little bit. How about 0.6? Rewriting that as a fraction, we can write 6 over 10, or it actually reduces down to 3/5. So currently we have x to the negative 3/5. One thing we did always say is when we have a negative exponent, we can bring it to the other side. So that means this is equivalent to 1 over x to the 3/5. Again, we do not want to leave it as x to the power of a number. We'd rather have a radical. So then, again, the number on the bottom, this 5 right here, acts as the index. So it's the 5th root of x to the 3rd. So this would be our final answer. Now going in reverse, rewriting each of the following expressions in exponential notation. So actually, I usually see this as easier. The end goal is this, x to the power of a number. If I just reverse the rules, this index is going to be the denominator of a fraction, and this exponent is going to be the numerator of a fraction. So as a result, we're going to have x to the power of 4/5. Very similarly here, the only thing I'm going to include is that this is currently x to the 1st power. And because it's x to the first power, is going to help us establish which one's the numerator, which one's the denominator. We know we have 1 in the numerator, 9 in the denominator. And again, the radicand, the term inside, is an x. But because, again, it's on the opposite side of the fractions below, we're going to compensate by putting a negative exponent right there. Okay, for the logarithms. So we have here 8 logarithms. You should be able to get to the point where you answer these very, very, very quickly. It might take a little bit of side work to kind of establish the relationship between the base and the term inside the logarithm, but you should be able to figure it out. So the way we're going to treat this is whenever I see log base 3 of 9, really the question I'm asking myself is 3 to what exponent equals 9? If we think about it this way, it's pretty easy to say, hey, x has to be 2, so log base 3 of 9 is 2. For the next one, log base 2 of 32. So in my head, I'm already asking myself, what is, or 2 to what power would give me 32? 2 to what power gives me 32? Well, you might have to practice this, but if we go through the powers, 2 to the first is 2, times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So that means 2 to the 5th power is 32. Those two, you should be able to get to a point where you can count, evaluate those in your head. The next couple ones, they might get a little difficult, but we're going to write out a few things to help us out. No, the rules haven't changed for letter C. Log base 25 of 1 over 125. It's me asking 25 to what power equals 1 over 125. Now, 25 to the power of 1 is 25. 25 to the power of 2 is much, much, much larger. So what we're going to try to figure out is there a common base between these two numbers? Well, there is. It's 5. So what we can do is we can write this as, or the left side, rather, I'm going to write it as 25 is 5 squared to the power of x. So again, power to a power, we're just going to multiply. And then 125 is 5 to the third, but because it's in the denominator, we're going to make a negative right there. Well, since we have the same base, 5 on the left side, 5 on the right side, the only things that have to equate are the exponents. 2x has to equal negative 3, and then using basic algebra, we can say x equals negative 3/2, which is the answer to this. Similarly, we're going to do letter D. One thing I'm going to do before we attack this is when I see this 4 right here in the exponent, let me highlight it. Anytime I have an exponent inside a logarithm, outside means something different, but if it's inside the logarithm, we can drag it out front. That'll make things just a little bit easier because now we have 4 times log base 6 of 36. Log base 6 of 36 is an easy question. 6 to what power equals 36? In your head, you know that's 2, so then I have 4 times 2. The answer is 8. Letter E, I have log base 5 of 4th root of 25. Now, if we remember, the 4th root of 25, this is what we just practiced in the earlier examples, is the same thing as 25 to the 1/4. Because if I want to rewrite a radical notation to exponential form, I can write it as an exponent, but it's going to be a 1/4. That would be the same thing as having, again, another exponent inside the logarithm, which means I could pull it out front. So right now I have 1/4 of log base 5 of 25. Again, that 4th root was an exponent of 1/4. We drag that out front, and then we don't have to worry about it as much as long as we evaluate the log. Log base 5 of 25, 5 to what power equals 25? That's 2 again. So what is 1/4 of 2? The answer is 1/2. I'm going to take that same information from before and actually apply it right away. The 5th root I see it inside the logarithm. I'm going to pull it out front. 1/5 of log base 4 of 16. 4 to what power equals 16? Again, 2. So then the answer is 2/5. All right, last two, we're looking at natural log. The only difference between a logarithm and a natural log is that a natural log has a base e. It's already implied a base e. So if we know that it has a base e, all we have to do is worry about how to rewrite this. E to what power equals 1 over e cubed. Using all our properties of exponents, if I want a number, or if I want a term to go into the opposite side or the denominator, we're going to have a negative exponent. So we already know it's going to be negative. And then, well, the exponent has to be a 3 in order to make that e to the third on the bottom. So then the answer is -3. Same thing here. The base is also e. So then we're asking ourselves, e to what power is equal to the 6th root of e? Using our rules, we know that 6th root of e is the same as e to the 1/6. So then the answer must be 1/6. All right, let's go into solving some logarithms, or first simplifying some expressions. The rules are very simple, but you have to follow the rules. A lot of students will mess up just because of the rules on the mastery. It says write each of the following expressions as a single logarithm. As a single logarithm. That means your final answer should be log of something or natural log of something. Okay, you need to have the log or the natural log, and you have to have something on the inside, but you shouldn't have multiple. It's a single logarithm. Well, the first thing we ever do when we combine or condense logarithms is make sure we have no coefficients. Well, so how do we get rid of this 2 and how do we get rid of this 4? The properties of logarithms say we can take any coefficient and bring that in as an exponent. So the natural log of x minus the natural log of y squared plus the natural log of z to the 4th. Okay, so now I have natural log, natural log, natural log. Anything that's being added immediately means multiplication. Anything that's being subtracted means division, but it's just that one term that I multiply or just that one term that I divide. So when I'm going to combine these, it's natural log. You need to have the natural log. I have an x inside from here. What I'm going to do is I'm going to divide because of this subtraction. That means this term, the y squared, is going to be divided. So I'm going to have over y squared. And then this is where students often make a mistake. This term is added, so that's going to be multiplied. But then some students think about where do I multiply, on top, on bottom? It's always going to be on top. Whenever you multiply a number or any fraction by a number, it's always multiplied on top. So that means z to the 4th goes on top, and that's your final answer. Another way to discern what should be on top and what should be on the bottom is anything that's positive. This is a positive natural log. This is a positive natural log. Both those terms are on the top. This is a negative natural log. That term goes on the bottom. So when I look at this next one, I see log of x cubed minus log of x minus 4. So then I'm going to have log of, but then since I have nothing in front, I don't have to worry about bringing in any exponents. This is positive, so that means the term on the inside, x cubed, goes on top. This is negative, so that means the term, or in this case, the binomial, x minus 4 goes on the bottom, and that's our final answer. Going in reverse, expanding each of the logarithm into a sum or difference, just says take anything that's on the inside. If it's being multiplied on the inside, you want to turn that into an addition of 2 logs. If you have anything that's being divided on the inside, you want to subtract that log. I see 3 terms on the inside, A, B, and C. So that means I'm going to have a total of 3 logs. Log, log, log. In the first log, I'm going to put A to the 5th. In the next log, I'm going to write B. In the last log, I'm going to write C squared. Now, the first log is going to be positive because the A is on top. The next log is also going to be positive because the B is on top. The last log is going to have to be negative because I'm dividing by C squared. This can't be our final answer. Our final answer is not allowed to have any exponents on the inside. So one thing I'm going to do is I'm going to write the 5th or 5 times log of A plus, now there's nothing to take out in the next term, but in the last one, 2 times log of C. That's our final answer for 6, Roman numeral 1. Very similarly in Roman numeral 2, I have 2 terms, so then it's just natural log of the square root of y minus the natural log of x squared. The second term is much more obvious. Take the 2 exponent, bring it out front. But in the first term, I do have to get rid of that square root. The way I'm going to get rid of that square root is, well, that has an index of 2 and an exponent of 1. So that means I have a 1/2 exponent. So then I'm going to drag that out in front, natural log of y. That would be our final answer for Roman numeral 2. And finally, let's solve numbers 7, and it's just 7 and 8 in this case. So if we're solving, the goal is get x by itself. Everything relies on inverse operations. So easy things to get rid of. Let's get rid of this minus 15. It's easy to get rid of that, the 15 from the side with the x on it. So the way to get rid of the inverse of, or the way to get rid of subtracting 15 is the inverse, which is addition, adding 15. Which gives us 25. Okay, the next thing, the easiest thing to get rid of is the 3. So I'm going to divide both sides by 3. This is where students tend to get nervous. Understand that, yes, you are allowed to have fractions like this. It may not be ideal, but it is what it is. So now I have 4 to the power of x minus 2 equals 25 over 3. You have to understand, if I want to get rid of a base of 4, the way to get rid of a base of 4 is using a logarithm with the same base. That means I'll have log base 4 of 25 over 3 is equal to x minus 2. You can see I took this base, and that turned into the base of the log. And I took this 25 over 3, and that went inside the log, which released x minus 2 by itself. You have to know that identity. Finally, just ask yourself, what is that one last step to get x by itself? Add 2. So as unpleasant as an answer might look, that would be your final answer, and you are allowed to leave it like that. I am not expecting a decimal answer because this is a no calculator portion, and you are not expected to simplify that either. In the next one, we could do a lot of the same work. First thing I'm going to do is I'm going to subtract 13. So then I have negative 6 is equal to 5x equals negative 6. Divide both sides by negative 6. So that means e to the 5x is equal to 1. Again, I want to get rid of the base of e. If I want to get rid of a base, I have to use a logarithm. So log base e, which actually means I could just use natural log of 1 is equal to 5x. Now, solve for x. How do I get that by itself? It would be dividing by 5. So then x would equal natural log of 1 over 5. There is an expectation in this class. You know some basic identities or basic values. For example, you should know the natural log of 1. natural log of 1 would always equal 0. Log of 1 equals 0 because e to what power gives you 1? The answer is always 0. 0 divided by 5 is still 0. So that answer is 0. That concludes the mastery topic number 3, exponents and logs. Hopefully this helped. Good luck on the summer math packet, and make sure you ask your teacher if you have any questions.